Hello and welcome back to Find Solve Explained. Today we're going to be doing a walkthrough and explanation of the first question from the 2019 British Maths Olympiad Round 2. So the question is as follows. Let ABC be a triangle. Let L be the line through B perpendicular to AB. The perpendicular from A to BC meets L at the point D. The perpendicular bisector of BC meets L at the point P. Let E be the foot of the perpendicular from D to AC. Now we need to prove that triangle BPE is isosceles. When you do a BMO2 geometry question, the first thing you want to do is draw a big, clear diagram, so that you can see all the angles and it's clear whether two triangles are similar or not, or whether they're isosceles. The second thing to note when you're doing geometry in BMO2 is that often, especially when there are loads of perpendicular lines and similar triangles, circle theorems are the big key thing. And to do a question like this, you want to prove something that is easier, that was sufficient to prove the claim. So for example, we want to prove something that would be sufficient to prove that the triangle BPE is isosceles. So we're kind of working backwards to make the question easier. So in this case, I'm thinking about what if we can show that E and B lie on a circle centered at P. It kind of looks like this, and it must be true if BPE is isosceles. But not only that, if we can prove that it lies on a circle, since both EP and BP would be radii, they would be equal, meaning that the triangle BPE would be isosceles. It also looks like, when you look at this circle, it goes through C. So what if we could show that this circle is in fact the circumcircle of the triangle BCE? In fact, it also looks like AB is tangent to this circle. Could we prove this by alternate segment theorem? In fact, if we did prove this, it would be sufficient to show that P is the center of the circumcircle of triangle BCE. That's because the center has to be on the line L. So since the radius of a circle at a point is always perpendicular to the tangent at that point. And because the center has to be on the perpendicular bisector of BC, since the circumcenter of a triangle is where the perpendicular bisectors of the sides of a triangle meet. And I'd like to remind you that P is by definition where the perpendicular bisector of BC meets L at the point P. To prove that AB is tangent to the circle at B, we need to prove that ABC equals BEC, and this would prove it by alternate segment theorem, which should be one of your immediate thoughts when you see a tangent. Okay, so now let's try and find ABC equals BEC. Try and prove that, because it seems much more manageable than proving that two sides are equal. The first thing to note is that ABDE must be cyclic, since AED plus ABD, so opposite angles, add up to 180 degrees, since they're both 90 degrees. Next, we can just start angle chasing. So if we pick an angle kind of arbitrarily, I'll pick ABC because it's the first one in the alphabet, then we can chase it and see if we can somehow prove that ABC equals BEC. So first thing we can do is we can find that BAD equals 90 degrees minus ABC. And from the circle that we found, since ABDE is cyclic, we know that BED equals BAD due to same segment theorem on the arc BD. Next, we can show that therefore BED equals 90 degrees minus ABC, since BED equals BAD, which equals 90 degrees minus ABC. Next, we can show that BEC equals 90 degrees minus BED, since angle AED is 90 degrees. From this, we know that BEC equals 90 minus 90 degrees minus ABC, which equals ABC. And if you look at the top thing in pink, that's exactly what we needed to prove, that BEC equals ABC. So we've done everything to prove that it's a tangent of the circumcircle of BEC, so AB is the tangent, and that P must therefore be the center of the circle which goes through B and E, meaning that PB and PE, or EP and BP as I called them before, are both radii, meaning that the triangle BPE is isosceles. So we've proved all that is necessary to prove that triangle BPE is isosceles, and we've finished the question. Now all you need to do is write it in the more logical order, so angle chasing first and then tangent stuff, etc. The reason why I kept angle chasing for last is because often you can waste a lot of time just aimlessly angle chasing. When you save it to last and you have a definite thing that you need to prove, like in this example ABC equals BEC, you can often do everything a lot faster, and when you've got multiple questions to solve, speed is actually quite important. You think it's not, but if you're aiming to solve a lot of them, you really want to be quick. Thank you for listening. If this video was helpful, comment down below, because this is a first kind of walkthrough video I've done. And if you enjoyed it, give it a thumbs up, maybe subscribe. Thank you.